So first we see what is meant by tall buildings and why we need tall buildings. You know, the reason for constructing tall buildings, especially in cities where the land is expensive and it does not allow us to expand horizontally. So in such situations, people consider that it's worth having buildings with so many stories so that a large number of people can be accommodated. So the tall buildings can be constructed as office buildings, residential space, commercial space. Commercial space means supermarkets, shopping complexes, and so on. So, and some of the buildings could be only apartment buildings, or else you might get some buildings as office buildings. But in certain situations, you can consider so many different things in one building. Maybe in the lower floors, you will get the car park. And as you go to the above the car parks, you might get shopping mall. Then you can get a number of office floors. And then finally, you might get a hotel or apartment. So can you give few examples of such buildings in Colombo? If you take World Trade Center, what is the type of building? So, so basically, if you look at construction loads, now if you are designing for an imposed load of 2.5 partitions, finishers, one each, the total is 4.5 kilonewtons per meter squared. Whereas, what is the weight of the slab during construction? Without the weight of formwork, the weight of concrete alone can be 5 kilonewtons per meter squared. So there may be situations where the weight of the concrete and the formwork can be more than the load that you have considered for the design of slabs. So in such situations, there is a possibility that the slabs can be overloaded. Slabs can be overloaded. So because of that reason, it's important that we consider the construction loads, or the loads that we lack during construction when we are doing the designs. So what is the type of deflection that you can get in a tall building? There can be two types of deflection. One is, you know, for example, when you take a tall building, the tall building is fixed at the foundation. The tall building is fixed at the foundation. So because the tall building is fixed, we consider it fixed at the foundation or the ground level. It basically acts like a cantilever. Basically acts like a cantilever. So because it's a cantilever, there can be a deflection at the top of the building. There can be a deflection at the top of the building. So that is the overall deflection. In addition to that, if you take two floors next to each other, then you will find there can be a relative displacement between two consecutive floors. There can be a relative displacement between two consecutive floors. The reason is the upper floor is subjected to wind, which is, and because of that, the upper floor tends to move relative to the lower floor. So because of that reason, we can get a relative movement. And this relative movement is called interstory drift. Interstory drift. And we have to limit the interstory drift to something like height over 400 to make sure proper functioning of the non-structural components like elevators. To make sure that the lifts are properly can function properly, we have to limit what we call interstory drift or the deflection of a flow with respect to the flow below. We have to limit that to something like height over 400. And sometimes even height over 300 may be okay. But height over 400 can be considered as a very good value. So, and in addition to that, what will happen if one flow moves with relative to the other too much? Then you will find all the partitions also can suffer certain amount of cracking. So to prevent that happening, we have to again ensure that this interstory drift is controlled, and this height of 400 is a good value to prevent excessive cracking in the non-load bearing elements like partitions. And then the other important situation is, because the tall building is a cantilever, the tall building tends to move. So if you consider the movement of the mouse that you can see, first the building will start moving in one direction, then it will come back, and when it come back to the center, it cannot stop, it has to go back, and then it will come back again. So basically the building will be moving in one direction and then come back to the center and continue to move. So because the building is moving like this, when the building moves to the extreme end, why it returns? It returns due to the stiffness. But as it slows down, there will be an acceleration on the building. And then when it comes back at the center, you will get the maximum velocity. And as you go to the end, again, you will get the maximum acceleration. So this acceleration can be felt by people. So when you are designing a building, again, you have to make sure this acceleration is controlled. So there are methods given in codes to approximately determine the wind-induced acceleration. So we have to calculate those accelerations and ensure that the movement of the building is controlled to the extent that the accelerations will not be felt by most of the people occupying the building. And so generally, when you are designing, when we design for wind loads, we consider ultimate limit state. Whereas when we design for the acceleration, we can actually check the acceleration of the building for a relatively lower speed, Something like, say, for example, if you are designing the building for 33 or 38 meters per second in Colombo, you can actually check the acceleration for a more probable wind speed of something like 25 meters per second. And when you consider 25 meters per second, what is the equivalent speed in kilometers per hour? Who is Kabila or Chaturanga? Are you there? Chaturanga? Are you there, Chaturanga? For Buddhika? Can somebody give the answer? If you are designing for 25 meters per second, what is the corresponding speed in kilometers per hour?
90 kilometers per hour.
90 kilometers per hour, yes. So you can see even 90 kilometers per hour is not a wind that will occur every day. So you can actually check the acceleration for a value like that. So then in addition to the interstory drift, we can get another definition which is called drift index. So drift index is an important parameter that allow an estimate of the lateral stiffness of the building. So that is actually based on the maximum deflection that occur at the top of the building due to the lateral loads. And the maximum value of drift index is about 1/500. So you have to make sure that the deflection that occur at the top of the building divided by the height of the building is less than 1/500. And this drift index is very important in modern buildings. The reason is, in new buildings, generally, we don't go for permanent partitions, except in apartment buildings. So when you don't have permanent partitions, most of the partitions will be out of lightweight materials. So because of that, the contribution of partitions to the strength of the building is very minimum. It's very minimum. So because of that reason, the modern buildings tend to be more flexible than old buildings, which are having fairly heavy members and also lot of permanent partitions. So because of this reason, the partitions do not contribute to the strength of the building in modern buildings. So we have to carefully check the deflection or drift index, and we have to ensure that the drift index is less than 1/500. So as I explained earlier, so a building can be subjected to wind-induced movements. And when we talk about wind-induced movements, in a tall building, we can get a wind acting in two directions. One is the direction of the wind, but because the building is slender and tall, what happens is when you have heavy wind, the wind will start forming negative pressure on one side of the building, and in the next moment it will form negative pressure on the other side of the building. So these negative pressure zones occur perpendicular to the wind direction. So generally when the wind is blowing in, say, X direction, we expect the building to move in X direction. But in the case of tall buildings, not only in the X direction, the building can start moving in Y direction as well. And that is due to the negative pressure zones that occur on either side of the building. And these negative pressure zones are called vortex shedding. Vortex shedding. So vortex is a negative pressure zone. And what happens is when the negative pressure zone occurs, the building is attracted towards that side. But at the same time, you'll find the negative pressure, these vortices pass in the building. And then the vortices will start forming on the other side of the building. So because of that reason, a tall building will be subjected to a lateral movement not only in X direction, that is the wind direction, it will move in the Y direction as well. So if you take the complete movement of the building, you will find that the building is moving in X direction and Y direction both, which means the building will be moving in an elliptical path, not in a straight line. The reason is all the time, the building will be moving either in one direction or the other direction in addition to the wind direction. So it will be moving in an elliptical path. So because the building is moving in an elliptical path, you will find that the occupants might feel this movement. And if the movement is excessive, you might find that it's difficult to do work at a desk, seated on a chair, because the building movement can be felt by the people. So this movement can have psychological and physiological effects, because what happens is when the building is moving, if there's another building that moves in the other direction, then people will see this movement of the buildings and they might not like it. Whereas those who had this experience might be looking for it all the time, and they become people who are sensitive to the wind-induced movements in the buildings. So that also can become a problem, and the building might have a bad reputation if the building is moving too much. Then how about the foundations of a building? So due to the height of the building, there will be fairly high loads transferred to the foundation. And so the foundation has to be designed to carry these loads to the underlying soil or rock layers, generally by using piles. And caisson is a large diameter pile, but it is hollow. So caissons are generally used in bridge construction, whereas piles are generally used in building construction. And piles can be used in bridge construction as well. But generally, we might not be using caissons a lot in building construction. The reason is buildings are subjected to heavy loads. And because of that reason, the pile foundations can be better suited for the buildings. And then in addition to that, sometimes, you might have 2 or 3 floors of basements in a building. But when it comes to the kind of the geological formations in main city like Colombo, you'll find to a certain extent we are lucky. The reason is bedrock can be reached within 20 to 30 meters in most of the locations, and certain places it can go up to about 40 to 50 meters as well. So one of the advantages, we have good firm rock strata on which the buildings can be located. But at the same time, certain locations, you will find that, the soil conditions in the top part of the top layers can be very bad. Sometimes you get peat layers and so on. So in such situations, you have to be careful to assess and see whether the negative skin frictions can develop and add more loads onto the piles. Right. So let's have a look at different types of buildings. So when we look at office building, generally we go with the open plan form, and the partitions are lightweight, and because the space available for renting is so important, we then generally tend to locate all the services in a central core, as you have learned for building engineering. And can I ask a question, Janit? Have all these students taken building engineering, those who are following large structures?
Yes, sir, I think so.
Yeah, right. Okay. Then so basically in office buildings you will get all the services grouped together in a central core, and so to distribute the services, generally we like to have a false ceiling, and within this ceiling we have to hide the services and especially the air conditioning ducts. And it is also preferred to have a floor to ceiling height of about 2.7 meters and a ceiling space of about 0.3 meters. And then we'll have a structural system. If you are going with beam slab system, generally the height of the beams would be limited to about 0.6 meters. So what will be the total minimum floor to floor height that you can get in a typical building having beam slab construction? So you get 2.7 meters plus 0.3 meters for services plus another 0.6 meters for structural members. So you'll end up with a floor to floor height of about 3.6 meters in a typical office building. And sometimes you might find that the floor to floor height can be as high as 3.75 meters as well. That gives more space for services, but the downside is that, you know, the height of the building will increase. But on the other hand, when you go with flat slab type construction, so with 300 to 350 millimeters for the ceiling, the false ceiling, you may be able to have another slab thickness of only about 200 millimeters for the flat slab, which means you can end up with a floor to floor height of about 3.2 meters. So then you'll ask why the flat slabs could be preferred. In some countries, flat slab is the preferred mode of construction. The reason is the flat slabs can be constructed easily than the beam slab construction because everything is flat. But the problem is at locations like washrooms, you have to drop the slab. So if it can be accommodated, then flat slab can be a suitable solution. And in addition to that, you know, when you use flat slabs, it is possible to go for pre-stressed concrete construction. It is possible to go for pre-stressed concrete construction, and the slabs pre-stressed can become fairly robust and economical. May not be strictly in Sri Lankan conditions, but in many countries, because the labor is so expensive in most of the countries, they have found flat slabs can be a very good solution. And sometimes you might go with two-way pre-stressing as well. So this way you can get building that is shorter than a typical beam slab type building. Then we'll also look at the apartment buildings. So the tall buildings can be designed for apartments or hotels. And when you have apartments or hotel in a tall building, sometimes the partitions can be of permanent type. So the other thing that you generally observe is that all the floors might have the similar arrangement, which means the partitions generally tend to repeat at each floor level. So because we have so many partitions, there can be two options for apartment buildings. One is to go with columns on a certain grid, and then to have the primary beams and secondary beams transferring the loads onto the columns. So that is one option. The other option is, because we are having so many partitions, some of the load carrying members can be hidden within the partitions. So it's common to see apartment buildings having a reasonable number of vertical walls, arranged at the partitions, and then in doing so, we can actually control the span of the slabs to desirable level, so that you will be able to construct the apartment building with a preferred floor-to-floor height like 3 to 3.2 meters. And in an apartment building also, it's necessary to provide the height to the ceiling of about 2.7 meters. But in apartment buildings, we generally do not try to have a ceiling. So even with 2.7 meter the floor to ceiling height or floor to floor height, plus another allowance for the structural system. If it is beam slab system, sometimes you will find something like 0.5 meters may be sufficient. And if it is a flat slab system, you might find something like 200 millimeters may be sufficient. Then you can actually have a floor to floor height of 3 to 3.2 meters or 3 to 3.3 meters in apartment buildings. Now, another thing that you see in apartment buildings is the washrooms all may be arranged at various locations within the apartment, and at each washroom we generally tend to have a shaft within which the services can be accommodated. So because of this reason, we do not need a false ceiling to hide the services. So in apartment buildings, because of this reason, we can end up with 3 to 3.2 meter floor height. So if you have an office building with 3.6 meter floor height, an apartment building with 3.2 meter floor to floor height, then at each floor level, you can save 0.4 meters. And this 0.4 meters, say you have 40 floors, 0.4 multiplied by 40 is 16 meters. And this 16 meters will be equivalent to something like 4.4 floors, little more than 4 floors. So you can see the same building of same height, same number of floors. An apartment building can be shorter than an office building. So this has a particular advantage. The reason is when the building is shorter by 4 floors, then it's like, you know, the load equivalent to 4 floors, or maybe less than that, because we are not having a slab all the time. Maybe the weight of 2 floors can be saved. And also, when you look at the facade, you will see that the total height of the facade is also can be reduced when you reduce the floor to floor height. So what you can gather from this is, we prefer the floor to floor heights to remain as low as possible, but we have to ensure that the arrangement satisfy the building regulations. And the building regulation states, when the office is fully air conditioned, if you want, you can go for 2.4 meters. But generally, a height like 2.7 meters is preferred. In houses also, you need 2.7 meters, but sometimes little more than 2.7 meters is also maybe the preferred height. So you can see the height of the building can vary depending on whether it's an office building or apartment building. Right. So with that background, we'll look at all different types of structural forms that we can use in tall buildings. And there are so many forms, but the most important point about all these different arrangements is that the apartment building or the office building should be able to resist the wind loads acting on it. So for that, we have to see how all these different structural forms can be made effective. So we'll look at all these different types of structural forms. So first we look at brace frame structures. So what you call brace frame structures. And here what we do is we use some diagonal members to resist the lateral loads. We use some diagonal members to resist the lateral loads. And this type of construction is particularly suitable for steel buildings. So the question is, have you seen this type of buildings in Sri Lanka? The answer may be that, it's not very common, because we do not use a lot of steel for large buildings in Sri Lanka. Then again, you'll ask why we don't use steel. What is the answer? Kabila?
So, maybe the corrosion problem for
Yeah,
long
corrosion
term
may
use.
be one problem, but it can be handled with painting. But the reason for going for steel going for concrete structures instead of steel is mainly due to the type of construction methods we have used. That's one reason. The other reason is the steel is imported. So steel tend to be a little more expensive in Sri Lanka. So because of that reason, you'll find that, still we are not using steel to a great extent in buildings except warehouse type buildings. So in this system, now you can see the vertical columns, the horizontal beams, and in addition to that, you can also see some diagonal members. So the lateral resistance is provided by the diagonal members that act together with the main members supporting the floors. So if you look at diagonal members, you can see we are now talking about a truss fixed at the base, and spanning vertically. Now you are familiar with the trusses spanning horizontally, but here there's an exception where the truss is spanning vertically. So in this system, now these columns are equivalent to the top chord and bottom chord of a horizontal truss. These columns are equivalent to the top chord and the bottom chord of a horizontal truss, and this forms a deep truss, and hence the system will be highly efficiently resisting the lateral loads. And then you also see there are diagonal members, and these diagonal members can be subjected by the tension or compression depending on the direction of the load. So because of that reason, we prefer steel for diagonal members. So if you look at different types of bracings, you can get double diagonal bracing like this one, or double diagonal bracing like this one here, or it could be something like chevron or K bracings. Here you can see it's called a K bracing. And also there's another type called knee bracing, and here you can see it's a knee bracing. So when you go with K bracing or chevrons or knee bracing, what actually happens is these horizontal members can be subjected to additional bending moments. The horizontal members can be subjected to additional bending moments. But can somebody say what is the main disadvantage of these bracing systems? So when you have the bracings like this, can you have openings? So in this type of situation, having an opening is not easy. Even here, it's not easy. But in this situation, it may be possible to have openings here. So one of the main disadvantages of bracings is that they conflict with the location of doors and windows. So because of that reason, generally we tend to arrange all these diagonal bracings around the lift core area, which is located centrally. So here you can see an enlarged diagram with chord members, bed members, and single diagonal brace in double diagonal chevrons and the knee bracings. So shall we stop the lecture